Well, in this module of Wave, I want to talk about some supplementary topics in traffic engineering that I believe they're useful for you to know and to also wrap up everything in our Wave module in the best possible way. These topics, so we are going to learn about three main topics, three important topics in traffic engineering. We are learning about human factors in traffic engineering, level of service analysis, and also intelligent transportation systems. So by the end of this lecture, you will obtain information about each one of them. You will learn about human factors in terms of their abilities, limitations, and how it impact transportation design. You will be able to explain roles of signifiers, constraints, and feedback in user interaction, going back to that human factor design. You will be able to differentiate based on different types, hierarchy of the roadways, and how level of service analysis is applied to them. And you will be also able to summarize the main components that are related to the definition of each one of these facilities. Let's start with human factors. Why do we need to know about human factors? Let me start with this example. Imagine flow of water in a pipe or in an open channel. Water will always behave similarly, and every particle, every drop of water will behave similarly. Now think about flow of traffic, which is consisted of individual drivers. Now these drivers may react very differently from each other, even under similar conditions. I'm sure you've been all in that situation when you're driving and you're approaching a traffic light and signal changes to yellow and you don't know what to do. Do I have enough time to cross? Or do I have enough space to stop? And you will make a decision, and the driver on the adjacent lane will make a completely different decision. You may decide to stop, and they may decide to go. Same condition, same roadway, and two drivers with very, very different decisions. Why that happens? A lot of that goes back to human factors. So, what is your experience as a driver? What is your level of risk taking? Or even some demographic characteristics like gender, like age. These are the things that will play a role. And that makes our design, that makes our job very difficult to consider all of these things at the same time in the transportation network. So we must know about human factors. But what is human factor? So human factor is a body of knowledge that considers human abilities, also human limitations, and will connect them with human characteristics. And when we consider all of these things in our design, so human factors, when it comes to our design, whether it is designing a tool or designing a machine or a system, or in our case, related to our workshop, designing an autonomous vehicle, we must consider these human factors. Now, when we talked about traffic engineering, traffic control devices, I already talked a little bit about human factors. I told you in how many ways we actually try to communicate a message with different tools in different ways. Like if I have a stop sign, not only I will use a unique shape, but also I will use red color, which is sending a prohibition, sending an alarm to drivers, right? We are also writing stop in that on that sign, and we are also writing stop on the pavement. So different ways to accommodate human factors, different perceptions, different characteristics of drivers. Or we talked about traffic lights, why red goes on top, because this is the most important message that should be conveyed. And we are all on the unanimous agreement that red is the most important message here. And also, it would be more visible if we put it on top of a traffic light. Whenever you are thinking of considering human factors in your design, you should remember one important fact. I love this book, The Design of Everyday Things. I have it in my library, and it has a very nice uh, quote, which says that, when you notice a bad design, when you're frustrated with the system, if there is a good design, you typically don't see it. So if you are using a system, and that system could be just like a mug, a coffee mug, your favorite coffee mug. You like it because it is in the right shape, it has a good handle, it is right size for the amount of coffee that you want to have. You never think about those things. You never think that, oh, this is a very good design because I can hold it very comfortably. But you know what? Think about this. If the handle was designed poorly, inappropriately, now this is where you will notice that bad design. So when we talk about human factors in our design, we should make sure that our design is actually not visible to our users so that it is gonna be serving their needs. Look at this example. Another example that I really like. This is from an old car to adjust the seat. So I would assume that one of them put the seat up and down, the other one front and back, and then probably the back to move the back. But this is very confusing. I have to try them. I don't initially understand what I have to do with them. I need to test them. But when I have a design like this that is completely created according to my expectations and my experience of sitting on a seat, then this is what we call a good design. You may never notice that, but this is what we want to be exactly the experience of our users when we consider human factors. Uh, Another example that is very relevant to our work is interaction of autonomous vehicles and road users and vulnerable road users like pedestrians, bicyclists. Like when you arrive at an intersection, let's say today you are riding your bike or you're walking and you arrive at an intersection and there is a vehicle at the stop sign. You will have some tools, some means to communicate with the driver. You make eye contacts, right? You will wave hands to identify, okay, I saw you. You can go, you can cross. But when it comes to autonomous vehicles, how can I make sure that I am detected by that autonomous vehicle? How can I make sure that I now have the right of way to cross the street if it is a mid-block crossing like the photo that you see here? How can I make sure about that? This goes back to what we call in human factor engineering as mental models, that we look at the experiences of people. We look at what they expect to happen. Maybe even that expectation could come from media. Maybe that expectation could come from real world experience. But whatever it is, we have to make sure that there is a way that we are fulfilling the needs of humans that are dealing with our system. Like in this case, try to be creative. Think about the ways that you can tell a pedestrian that I saw you, you're good to go. So maybe we can have just to be silly, we can have a giant robotic thumb on the on top of the car to show the pedestrian that you're detected, of course, it's not going to be the best design, right? Maybe a light, maybe a blue light on the car to tell the pedestrian that you're detected, maybe a sign. There could be, and there are, this is already at the research stage that people are looking into that to see what are the best ways that we can communicate a message between an autonomous vehicle and pedestrians and bicyclists and scooters, humans that are using the roadway. And whenever we are thinking about these, there are three rules that we must follow. I want to finish this topic with these three rules. Of course, there is much more into human factors. This was only a brief introduction to give you ideas about human factor engineering. So what are these three rules? We call them signifiers, constraints, and feedback. First of all, sometimes your experience or your understanding of a system might not be exactly what is going to happen next in using that system. Look at this roadway. You're driving, and this is going up. This is what we call a vertical alignment, but there happened to be also a horizontal curve right at the top of this vertical curve. So I have no idea how sharp this turn could be. What do I do? As a traffic engineer, I'll add a signifier here to tell the drivers that, okay, this is going to be a sharp turn. And even how sharp this arrow is will communicate that message again. So we have different types of arrows to be used. It could be just a very sharp left or something like this that is telling how sharp that turn is going to be and how they should expect to navigate it. As I'm talking about these things, I would like you to think about how to have a signifier when we are working on an autonomous vehicle design that is going to accommodate pedestrians and bicyclists in our roadway. Next thing would be constraints. Look at this roadway. This roadway could be wide enough, or it could be too wide that some drivers, vehicles might assume that, okay, I can use it. But this facility is not designed for those vehicles. It's pedestrian only facility or bicyclist facility. It's a bike trail. So what do? I'll make some constraints here as the barriers that you can see here to make sure that I prevent people that are not allowed to use this area to get into it. Another thing is what we call feedback system. Now, I'm sure you've been to signalized intersection where you want to cross and you push the button. Now, you may receive a feedback or you may not. The best system is where as soon as you push the button, there is an audible feedback that wait, or some sort of some audio that will tell you that, okay, you are detected and you need to wait. In some areas for bicycle detection, like in Portland or in Bay Area, they use blue lights on traffic lights to show bicyclists that you are detected. This is a feedback system. So when I'm thinking of an interaction of autonomous vehicles and humans and road users, vulnerable road users, I must think at least about these three rules: signifiers, constraints, and feedback. And I leave it to you to think about how to accommodate it in your design. Now, with that, so many times drivers' expectations and preferences and experiences are used to quantify performance of a traffic system, of a transportation system. This usually happens under a big umbrella that we call it level of service or LOS analysis. So level of service happens differently based on different facilities, which again goes back to your expectations of driving in those facilities. In traffic engineering, we have two different types of facilities. We call them uninterrupted flow versus interrupted flow. Uninterrupted flow means that I, as a traffic engineer, do not get involved directly with the movement of vehicles. I do not interrupt. It is the facility itself, like a freeway, like a highway. It is the number of lanes that are there. It is other vehicles that are on the roadway. You never see me as a traffic engineer with a traffic light or with a stop sign to tell drivers what to do. Versus in an interrupted flow, now I, as a traffic engineer, as a designer, get involved to interrupt the traffic, to make sure that there is an orderly flow movement in the traffic. How do I do that? Based on traffic control devices that we learned in previous classes, in previous modules. Now, my expectations would be different in when I'm driving on a freeway versus when I'm driving on a local street. Even when I'm driving on a freeway and I'm driving on a highway, my expectations are going to be different. So we will measure those expectations through the level of service analysis. And I want to talk about this level of service analysis for both uninterrupted and interrupted facilities, starting with uninterrupted facilities like freeways, highways, two-lane highways. When we talk about uninterrupted facilities, your driving experience goes back to your freedom to maneuver, goes back to how easy you can pick your speed. Like, if I want to drive, is my speed kind of limited to the vehicle in front of me, or I have all the freedom to pick my speed? Yeah, there is a speed limit. There could be some physical constraints like the geometric design, but am I free to choose my lane or am I free to choose my speed? We refer to them usually as car following and lane changing behavior of drivers. So if I measure those things and put them in a quantitative system to measure the performance of the system, measure performance of a freeway, highway, two-lane highway, multi-lane highway. This is what we call level of service analysis. And in traffic engineering, level of service analysis goes from A to F. So A means a system is working at its best condition, and F is the failure of the system. And as you can expect, level of service goes somewhere between these two ranges. Let me show you some examples. This is an example of level of service A. So you see that going back to the module that we talked about traffic flow, traffic stream parameters, one of the things we talked about was density. So density was number of cars that are occupying a 1 mile segment of a roadway, right? So you see that in the level of service A, we have a very, very low density, which is the best thing to measure the demand on a roadway. So at a very low density, you're able to, every one of these vehicles are able to pick their speed, their lane. You don't notice the presence of other vehicles. Now, as more and more vehicles are getting on the roadway, you probably start to see more vehicles in your rear mirror, side mirrors. Now they're more noticeable, but still the traffic condition is not impacted, or your choices is not impacted by the presence of other vehicles. Until we get to now the other levels, D, E, and F, that gradually more and more vehicles are getting on the roadway. So at level of service E and F, now we are working very closely to the capacity of the roadway. with a minor interruption in traffic. Like if there is let's say you are at level of service E, so you see there are lots of vehicles on the roadway, but still the system does not have major queuing. There is suddenly a driver who changes their lane, or there is a distracted driving. This will move everything from that uncongested, stable condition to congested, unstable condition. So now level of service F would be where we see formation and dissipation of queues again and again. So we want to quantify this system and see how a freeway or a highway is operating and whether it is at level of service A, B, C, D, or E or F. Now, in order to do that, we start with defining roadway hierarchies and roadway facilities. Like, as a road user, you might interchangeably use freeway and highways and roadways. But from traffic engineering standpoint, there is a clear definition behind each one of these facilities. Like, what is a freeway? Let's talk about it. A freeway is, first of all, a fully accessed control facility. It means that there should be no at-grade crossing. If you have to connect another roadway to a freeway, it must happen through on and off ramps. Most of the times, interchanges, right? And also, we should never connect a local street directly to a freeway. We will go through the hierarchies. Like when you get out of your house, you are probably let's say you're at a cul-de-sac. And from this cul-de-sac, you get into some local streets, and then you get into some collectors, and those collectors will get into arterials, and these arterials will get into highways, and highways will get into freeways. So as we are moving up, we see that the access is more restricted. So you would never see a driveway flowing into a freeway or a highway. So access is restricted, mobility is increased. And that mobility in terms of, for example, speed would be a good measure there. What else we have? At least 2 lanes in each direction, divided by a full median. This is probably one of the most important definitions of a freeway. The 2 directions of a freeway they have no interactions with each other. If you have to turn left, if you have to do U-turn, you need to go through one of the off and on ramps, one of the interchanges to do that. You probably have seen sometimes you're driving on, let's say, Interstate Highway 5, which is mostly at most sections, it turns into a freeway. Then there is a gap somewhere. And they say that, okay, you are not allowed to make any U-turns in this gap. This is only for emergency vehicles. This is for police officers. That is a definition of a freeway, that you are not allowed to make any at-grade crossings or interactions between the two sides. Freeways typically have higher standards, mostly in terms of speed, which then translates into geometric design, like what we learned in that geometric design module. And analysis assumes that traffic is unaffected by the merging or diverging if you are at the basic freeway segment. We have 3 different segments: basic freeway segment, merging, diverging, and weaving. It is outside the scope of our work. I'm just talking about the basic freeway segment here. How do we find level of service for a freeway? We define an ideal situation. We call it base condition. And then we see where is our existing condition. If our existing condition is close to that ideal condition, okay, it's level of service A, B, C. So as we get further away from that ideal condition, level of service is going down from A, that is that ideal condition, to F, which is the failure of the system. Now, how do we measure this difference? We look at the impact of non-ideal conditions on two things: free flow speed and flow rate, analysis flow rate. And then we measure density based on these two factors. The calculation and adjustment factors for these steps is outside the scope of our work for this module. I only want to give you some insights about what is an ideal freeway. So when we talk about that difference between the ideal freeway and existing condition, what exactly we are talking about? An ideal freeway is level terrain, flat roads. So a longitudinal grade of 2% or less would be an ideal situation. Remember, this is ideal. Does it mean that we are always dealing with ideal situations? Of course not. So many times you're driving on a freeway and you have very sharp, grades going up, right? That is non-ideal. So we have to see what would be the impact of that non-ideal situation. Wide lane width. So an ideal lane width for a for a freeway is 12 feet. If it is anything less than 12 feet, it will directly impact the speed. So it will negatively impact the speed. We never go below 10 feet for freeways. And also it is not practical. It's not a good practice to go above 16 feet, although we never even get close to that. But 16 feet, if you have wider lanes, what happens is that it will turn into two lanes, two travel lanes, and it will just confuse drivers. So 12 feet would be ideal. I'm talking about freeways. Sometimes in local roadways, we might even have very narrow travel lanes to make sure that we control the speed. One way, one strategy, although I'm not a fan of it, but one strategy to lower the speed would be narrower, wide lanes. The other thing is what happens on the right side of the freeway. This is what we call right shoulder. Shoulder is that buffer next to the roadway. It may or may not be paved, but it will give some freedom, some buffer to the drivers that are going on the freeway. So ideally, we should have a 6 feet clearance on the right side of a freeway. Ideal situation. Sometimes you're driving and suddenly there is a bridge with a limited right of way, right? And you're driving and the concrete barriers are next right and left side of the freeway without any buffer. This is not ideal. I have to see how much it will impact the human experience, perceptions of drivers on that roadway. Only passenger cars. Trucks are going to negatively impact system performance. So we have to see what percentage of trucks are there and what is their impact. Especially trucks are bad for the system performance when we are on grades, going up grades. Trucks are going to be crawling. I have to then figure out that what is the equivalency factor of trucks. So one truck in that situation is equivalent to how many passenger cars? Interchanges, ideal situation, they must be 6 miles or greater, 6 miles or more further away from each other, gapped out. Does it happen? No. Many times we have interchanges 1 mile, 2 miles, 3 miles. Then we have to count them and we have to consider their impact. And as I said, when we do that, when we define the ideal and when we look at the prevailing condition, we can figure out what would be the difference. And that difference would be defining level of service. Next thing that I want to talk about are level of service for multilane highways. But how multilane highways are different from freeways? That is, again, the technical part of that. The most important, so as you can see, we are usually talking about fewer number of lanes. Like, I wouldn't see a 10-lane facility as a multi-lane highway. Those higher capacity roadways, they are categorized as freeways. So multi-lane highways usually 4 or 6 lanes total of both directions. Usually lower posted speed limits, 40 to 60, I would say also 65 miles per hour. It's not unusual. But the most important thing is what happens with the median treatment. So whether uh, so you saw that for the freeways. What was the median? The two directions were physically separated. So there is either a huge buffer between the two directions, or there are physical barriers like concrete New Jerseys that are separating the two directions from each other. But for multi-lane highways, the two directions can in fact interact with each other. So it could be it could be a painted striping. It could be what we call a two-way left turn lane. In common language, it's also called suicide lanes, right? But the correct terminology for that is two-way left turn lanes. Or it could be a full median, similar to freeways, with the difference that there might be gaps in that median to allow for a left turn or to allow for a U-turn. So this is what we define as multi-lane highway. And of course, I forgot about this one, that there might be traffic lights, traffic signals. Most frequently, it happens in rural areas. Like if you have a multi-lane highway that is going through some rural areas, and then there is a recreational area, or maybe there is a residential area, a village that connects to this multi-lane highway because of safety concerns. Like if a vehicle wants to turn left or cross, because of safety concerns, we may have traffic lights. But the important thing is that we are still talking about uninterrupted facilities. These traffic lights should not create queues in the system such that they will turn into interrupted facilities. They only may exist because of safety issues. Then how we find the level of service is exactly similar to freeways. We define ideal situation and we see where is the prevailing condition compared to that ideal condition. What are the ideal conditions for a multi-lane highway? Level trains, similar to freeways. Lane width, still 12 feet would be ideal lane width. Here, because the two directions of a highway could interact with each other, we not only look at the right shoulder, that right buffer, we also look at the left shoulder. So we combine both of them. And in an ideal scenario, in an ideal situation, that combination should be 12 feet. 6 feet would be the ideal, right? If there is anything less than that, we have to see the impact again on the speed. There is no direct access points along the roadway. For multi-lane highways, access points could happen at grade. That's why we call them access points versus what we call in freeways, we call them ramp density. Here, it could be access points. Ideal situation, no access points. As we get more and more access points per mile, it will lower the speed. Divided directional traffic, ideal situation. Only passenger cars, no trucks, and a good free flow speed, high free flow speed of 60 miles per hour. Next facility that I want to introduce here are two-lane highways. So two-lane highways, one travel lane in each direction, typically not divided, used for lower traffic volume situations. They have similar, free flow speeds compared to multi-lane highways, somewhere between 45 to 65 miles per hour. They have wide range of design. What does that mean? If you are driving on a freeway, you should never see a sign that tells you to lower your speed because you're approaching a curve on the roadway. We have to design that curve in a way that it will accommodate the design speed that was true for the entire facility. You're driving 65 miles per hour on I-5. We must design our curves such that it will accommodate that speed. But sometimes you're driving on some roadways and you suddenly see a huge drop in the speed limit. It goes from 55 miles per hour to 35 miles per hour. Why? Because you're approaching a turn. You're approaching a horizontal curve. So Is it ideal? No. It is actually against drivers' expectancies, but it could happen on two-lane highways. And we should then measure what would be the impact of those non-ideal situations. May have occasional traffic signs or even stop signs. Like if you have a two-lane highway that is going through a residential area, and there are pedestrians who are crossing both sides of that two-lane highway. We will drop the speed going to 25 to 45 miles per hour, and then we'll either control it by traffic lights or stop signs. But the most important difference between multi-lane highways and freeways and two-lane highway is the ability to pass a slow-moving vehicle. On freeways and multi-lane highways, when you want to pass another vehicle, you have extra lanes to do it, right? For two-lane highway, you have to occupy the opposing lane to do that. And this will change the story because now, depending on how many times that lane is occupied or what are the available gaps, or how many times you are facing a crawling truck on your direction, or how many times you are not legally allowed to pass a car. No passing zones, right? If you're going up hills, vertical curves, and you don't have a good visibility of the other side, we will make passing prohibited. So depending on all these things, level of service would be impacted in two-lane highways in a different way that it was impacted in multi-lane highways and freeways. So, as I said, we have to consider both sides and the impact of train, and specifically the impact of train on heavy vehicles is going to play a more significant role. Here we may divide our roadways into different segments, like where there is no passing allowed, when there is a passing allowed, when there is an auxiliary lane. So many times we may add an auxiliary lane. We call it a passing lane. So we will move slower moving vehicles to the right lane, and then we will allow vehicles to pass them. The level of service analysis would be very different for each one of them. Some examples of, two-lane highways, like we have commuter routes. Commuter routes usually connect two urban areas with each other. Then if from this connector, from this commuter route, we want to connect to another land use, like there is a recreational park, there is a state park, there is a residential area. That route that will connect to those locations, we call it access route. And we also have through routes, which is part of that commuter routes, but when we are going through residential zones. And this is where we will actually apply those traffic lights and traffic signs. We will measure we'll consider the ideal situation, and we'll see what is the condition on our roadway. We will compare it with that ideal condition. So the ideal condition for a two-lane highway, level trains, again, wide lane width, 12 feet minimum, shoulder width, 6 feet. Again, we're only looking at the right side this time. No direct access points along roadway, only passenger cars. So this is a new thing, 0% no passing zones on the highway segment, which means that at any point, if you want to cross, you're technically allowed to do that. If you want to cross the lanes and occupy the opposing lane, you're allowed to do that. And of course, we are dealing with an uninterrupted facility, which means that if there is a stop sign, if there is a traffic light, it should not turn this facility into an interrupted facility. There should be no major queuing impact because of those traffic control devices. So everything up to here was about uninterrupted facilities. I told you at the beginning of this part that uninterrupted facilities means that I, as a traffic engineer, do not interrupt the traffic. It is the presence of other vehicles. It is the interaction of drivers with each other that dominates their experience. But for interrupted facilities like traffic lights, stop signs, roundabouts, now I am telling the drivers that, okay, now you have to stop. Now you're allowed to go. Now you're allowed to turn left. Now pedestrians can cross, right? So in those situations, we will use a different measure to quantify level of service, that is delay. So for the uninterrupted facilities, we were looking into free flow speed. We were looking into analysis flow rate, and we were developing density. Do you remember those 6 photos that I showed you, and they were showing number of cars? They were basically talking about different densities, right? So density no longer means anything at signalized intersections because we are talking about one node. We are talking about one point. We are not talking about a segment. So when we are talking about the point, the measure that we will use is going to be delay. What is the delay that is imposed to the vehicles? Now, when we talk about delay, there are different delays. Like this is what we call a time-space diagram. These are very useful tools in traffic engineering. We show like the time on x-axis and space where the cars are on the y-axis. Look at this car. As this car, and by the way, because this is time, this is space, so the slope of these lines that we call them trajectory of vehicles, this shows speed. So you see that this car was going with a constant speed as it was approaching a signalized intersection, and probably signal turns to red. So they started decelerating, and then they were stopping behind the red light, and then the signal turned green and they started accelerating, and they get into a constant speed after that. So depending on where we want to measure that delay, we may get different delays. We have a stopped delay, the time that the vehicle was completely standing still. We may have approach delay, which considers some sort of that deceleration and acceleration. But the most important thing, a theoretical concept that we will use for level of service analysis at signalized intersections, or usually at interrupted facilities, is what we call control delay. So control delay means that what is the average delay that is imposed to vehicles because of that control device, because of that traffic light, because of that stop sign, because of that roundabout. And this is not very easy. Some parts of that is easy to observe. Some parts of that goes back to more advanced models to figure out what would be the delay. In general, delay is consisted of 3 components. What we call average delay due to uniform arrival of vehicles, average delay due to random arrival of vehicles, and residual delay, basically. How to calculate these things, each one of them, there is a big theoretical body of knowledge behind each part of D1, D2, D3. It is outside the scope of our work. My hope was that for this section, you will learn that if we want to quantify level of service at signalized intersections, at interrupted facilities, delay is the measure that we use versus density that was used for uninterrupted facilities. And I want to finish this module by talking about intelligent transportation systems, or ITS. Why did I decide to finish this module and this wave on the transportation side with ITS is because if we draw a Venn diagram and we look at transportation engineering and electrical engineering, at the center of the intersect of these 2 areas, there is ITS. This is where we are actually using electrical engineering to improve everything that we talked about so far. to improve that human experience, to improve level of service. So basically, ITS is to use advanced technologies to improve transportation safety, efficiency, and sustainability. We can have multiple goals. Some key goals could be to reduce traffic congestion. How can I do that? If I could have a good detection in place, such that I have a clear idea of the demand at every single intersection in my network, I can optimize them. I can optimize the system performance. If I can improve the roadway safety. If there is a hazard on the roadway, that I can communicate it with drivers. I can enhance mobility, like making the level of service better. I'll work on some examples as I talk about them in next slides. Or reduce environmental impacts, which is a direct result of these enhancements in mobility. Some examples here, I have some examples for your review, like traffic control, traffic signal control systems, electronic toll collection. Just imagine the time that we had to pay $7 or just pay cash versus the time that now we just cross the plaza without stopping, just lowering our speed, and the system will capture the plates and will send us the bill. This is a good application that is reducing the traffic congestion, enhancing the mobility, improving safety. It is reducing environmental impact, right? Smart navigation systems that are available in cars. And if you're in California, I suggest you look at Caltrans PEMS database. It is a very fantastic, a very comprehensive, inclusive database that shows type of data that we can obtain through this ITS application and how we can use them to optimize the system performance. So I would suggest you to just Google PEMS, and you can create an account for free and look at the available data that Caltrans will suggest. When we talk about ITS, there are some principal components, some key enablers, like detection systems. How that detection is happening, it could happen through sensors, cameras, radars, lidars. So basically talking about the detection. And then the information that we obtain from this detection is going to be communicated between different components of our network, different units that are moving in our network, or maybe not moving. It could be vehicles or it could be infrastructure. And with that, we will make some decisions for the control. And we will need advanced data processing, because with ITS, we are usually dealing with big data and we are dealing with real-time data, and we need to make decisions. So integrating AI into that decision making would be very important. And of course, the key enabler here would be that the wireless communications between different components of our transportation network. And the most important feature of ITS for us, especially relevant to Wave, is what we call vehicle to everything, or V2X communications, that are supposed to work for the benefits of ITS, like improve safety, traffic efficiency, sustainability, and of course, the one that I want to emphasize here are autonomous vehicles. When we talk about vehicle to everything, what is everything? We can have vehicle to vehicle communications. We can have vehicle to infrastructure, vehicle to pedestrian, vehicle to network, vehicle to grid. And each one of them is going to serve a different purpose. Like if I'm working with vehicle to vehicle, What I'm trying to achieve is a communication between vehicles so that we would avoid collisions. I know that there is a sudden brake for one of those cars in the system, or a sudden change lane because there was an object on the roadway. So they are communicating with each other at any time. Vehicle to infrastructure, like I know if there is, I don't know if you've noticed this or not, sometimes you're driving and you see that there is a huge congestion on the other side of the freeway. And then you pass it and you see like downstream of that upstream of that congestion, there are some vehicles who are going super fast. They're going 75 miles per hour, although you know that in just a couple of minutes, they have to stay in that queue for a long time. Now, if I can communicate this to all the vehicles, and those vehicles, instead of going 75 miles per hour, let's make everyone go 35 miles per hour. So instead of bringing everyone to this deadlock, to this congestion, let's control the input until we can get the output to its usual condition. So if I can communicate that message, that would help the efficiency of the system. Vehicle to pedestrians, going back to that example that I had at the human factors, that if you have a pedestrian crossing the roadway, how can they communicate with an autonomous vehicle? One way would be your smartwatch. Think about it. There could be your smartwatch, there could be an app on it that is communicating with this autonomous vehicle at any time, and it will tell you what to do if you are detected or not. Vehicle to network, vehicle to grid. Like if you're driving an electrical car, EV, electric vehicle, and how it will communicate with the power grid to optimize it, to optimize your performance. This is another thing to consider. We're mostly when we talk about autonomous vehicles, I believe these first three, vehicle to vehicle, vehicle to infrastructure, and vehicle to pedestrian, are the topics that we have to focus. Communication technologies here, I've only listed them for you here because I'm sure you will learn about them in your electrical engineering courses. But this communication usually happens through DSRC, and as you can see, some other methods like 5G networks that could be helpful for this communication. And I would like to finish this with the benefits and future trends. The benefits exactly serve what was the purpose of the ITS. Fewer crashes, improve safety. If I can make sure that my car is communicating with the other cars, we can minimize the error. Less congestion on the roadway, improving the efficiency. Like if I can tell the drivers that I can talk to the traffic lights that as soon as this group of vehicles arrive at an intersection, give them green. And as they are moving through the intersections, keep them moving. Make a green wave for them, signal coordination, right? That would improve the efficiency of the system, which will then help on environmental issues like better fuel efficiency. And of course, if we are talking about future trends, if we are talking about autonomous vehicles, those autonomous vehicles would require smart infrastructure. They would require smart cities. They would require V2X to best perform. And I'm sure that in future we will learn more of the integration of AI and Internet of Things in these topics. Here is a list of references that were used for this module of WAVE.